Far out in the cold, dark reaches of our solar system, where sunlight is little more than a faint glimmer, Neptune defies logic. This distant blue giant, shrouded in swirling storms and winds that scream at speeds faster than a jet plane, holds a secret that has left scientists scratching their heads for decades. Despite receiving only a fraction of the Sun's warmth compared to Earth, Neptune somehow radiates more heat than it absorbs, a cosmic contradiction that challenges everything we think we know about planetary science. What could possibly be powering this icy behemoth from within? Picture a world where the Sun is nothing more than a bright star in the sky, barely offering enough warmth to pierce the eternal chill. Yet beneath Neptune's vibrant blue exterior, something is stirring, something energetic enough to generate heat that rivals what it gets from our distant star. This isn't just a curious anomaly. It's a fundamental mystery that could reshape our understanding of how planets form and evolve. Could there be hidden forces at work beneath those turbulent clouds, ancient radioactive elements decaying deep within its core, or perhaps processes we haven't even discovered yet? The answers might lie buried under layers of freezing hydrogen and helium, waiting to be uncovered. This is more than just a story about a planet. It's a detective story spanning centuries, from the first time astronomers peered at Neptune through their telescopes to the cutting-edge simulations running in labs today. Every clue we uncover brings us closer to solving one of space's most enduring riddles. And as we piece together the evidence, we'll explore not just what's heating Neptune from within, but what it tells us about the hidden workings of our solar system and beyond. So buckle up, because we're about to dive into the depths of this icy enigma, where the answers might be as strange and wondrous as Neptune itself. Neptune's heat imbalance isn't just a quirky fact, it's a cosmic head-scratcher that forces scientists to rethink how planets behave. At first glance, the math just doesn't add up. Imagine standing 30 times farther from a campfire than your friend. You'd barely feel its warmth, right? Yet Neptune, sitting in that same icy distance from the Sun, somehow manages to pump out 2.5 times more energy than it takes in. That's like a freezer producing its own heat while barely plugged in. So what's going on beneath those churning blue clouds? One leading theory points to Neptune's turbulent interior. Unlike rocky planets, gas giants don't have a solid surface to slow things down. Deep inside, hydrogen and helium swirl under crushing pressures, creating friction that could generate heat like rubbing your hands together on a cold day, but on a planetary scale. Then there's the possibility of leftover heat from Neptune's violent birth. When the planet first formed, colliding debris and gravitational forces may have supercharged its core with energy that's still slowly leaking out billions of years later. But here's where it gets even stranger. Uranus, Neptune's icy twin, orbits at a similar distance and should behave the same way, yet it barely emits any excess heat at all. This glaring difference hints that something uniquely active is happening inside Neptune, something we haven't fully unraveled. Could radioactive elements buried in its core be decaying and releasing energy? Or is there a hidden layer of exotic materials sinking deeper, generating heat through chemical reactions we've never observed? Every unanswered question pulls us deeper into the mystery, proving that even in our own solar system, the universe still has surprises up its sleeve. If radioactive decay can't explain Neptune's mysterious heat, what's really cooking inside this distant world? Scientists have their eyes on some fascinating possibilities, starting with the planet's violent origins. When Neptune first formed over 4 billion years ago, it was likely a scene of cosmic chaos. Countless chunks of ice, rock, and gas slammed together under immense gravity, releasing staggering amounts of energy in the process. That leftover heat from its birth might still be trapped deep within the planet, slowly seeping out like an ember from an ancient fire. But there's another player in this thermal mystery: gravity itself. Neptune's enormous mass creates crushing pressures in its interior, squeezing hydrogen and helium into bizarre states of matter we can barely replicate on Earth. This gravitational compression doesn't just create extreme conditions, it generates heat through a process called Kelvin-Helmholtz contraction. Think of it like pumping air into a bicycle tire. As you compress the gas inside, it warms up. Now imagine that happening on a planetary scale, with entire layers of Neptune's atmosphere pressing inward relentlessly. Then comes the wild-card exotic materials lurking in Neptune's depths. Some researchers speculate that beneath its swirling blue exterior, the planet might harbor substances like diamond rain or supersonic water, where oxygen forms a solid lattice while hydrogen ions flow freely. These strange states of matter could be releasing energy through chemical reactions we've never observed anywhere else. Even more intriguing is the possibility of methane breaking down under extreme pressure, forming heavier hydrocarbons that sink toward the core and release heat along the way. What makes these theories so compelling is how they challenge our understanding of planetary behavior. Neptune isn't just an outlier, it's a laboratory for physics that defies Earth-based expectations. Every new discovery about its internal heat forces us to reconsider what's possible in the universe's hidden corners. And with missions like the proposed Neptune Odyssey aiming to study the planet up close, we might finally get the data needed to crack this decades-old enigma wide open. Gravitational compression might sound like something out of a sci-fi novel, but it's one of the most plausible explanations for Neptune's mysterious heat. Picture the planet as a massive cosmic pressure cooker, where the sheer weight of its own atmosphere squeezes the interior with unimaginable force. This relentless compression heats up the gases inside through a process known as Kelvin-Helmholtz contraction, a phenomenon that occurs as Neptune gradually shrinks over billions of years. Every tiny contraction releases energy, much like a ball of dough warming up as you need it, only on a scale so vast it defies intuition. But here's the catch: the numbers don't quite add up. While Kelvin-Helmholtz contraction can explain some of Neptune's excess heat, calculations suggest it shouldn't account for all of it. If this process were the sole culprit, the planet would need to be shrinking far faster than current models predict. That leaves scientists wondering what else is lurking beneath those turbulent blue clouds, adding fuel to the fire. One clue lies in Neptune's tumultuous atmosphere. Unlike Uranus, its winds whip at supersonic speeds, stirring up deep layers of gas and creating friction that could generate additional heat. Imagine stirring a cup of coffee. The spoon creates tiny swirls that warm the liquid slightly. Now scale that up to a planet-wide churn, where entire oceans of hydrogen and helium collide under crushing pressures. The result, a hidden furnace buried beneath the storm. Yet even this doesn't fully solve the puzzle. Some researchers argue that Neptune's heat might come from a combination of sources: gravitational compression, atmospheric friction, and even residual energy from its violent formation. It's like trying to piece together a cosmic jigsaw where every fragment reveals a new layer of complexity. And with missions like the proposed Neptune Odyssey aiming to peer beneath those swirling clouds, we might finally get the data needed to separate fact from theory. Until then, this icy giant remains one of the solar system's most tantalizing enigmas. Neptune's fiery origins read like a cosmic creation myth, a violent, swirling chaos of gas, dust, and colliding planetesimals. 4.5 billion years ago, as the young solar system took shape, Neptune didn't form gently. It grew through relentless collisions, each impact adding mass and generating staggering amounts of heat. Picture a snowball rolling downhill, but instead of snow, it's gathering chunks of ice and rock the size of mountains, each collision sending shock waves through the growing planet. That energy didn't just vanish, it got trapped deep inside like a thermal battery charged during Neptune's most turbulent era. This leftover heat theory isn't unique to Neptune. Jupiter and Saturn also radiate more energy than they receive from the Sun, likely fueled by the same primordial furnace. But here's the twist: Neptune's heat output is disproportionately high for its size and distance. Jupiter, for example, is a behemoth with a massive core that should retain heat far longer, yet Neptune, smaller and farther from the Sun, punches above its weight thermally. This discrepancy suggests something else is at play beyond just residual formation energy. Uranus, Neptune's closest sibling in composition and orbit, adds another layer to the puzzle. Both ice giants formed under similar conditions, yet Uranus emits barely any excess heat. If primordial energy were the sole explanation, shouldn't they behave alike? This glaring difference hints that Neptune's heat isn't just a relic of its birth, it's being actively sustained. Some researchers propose that Neptune's deeper internal motions, like denser materials sinking toward its core, could be generating additional heat through friction. Imagine syrup slowly flowing through thick honey. The resistance creates warmth. On Neptune, that process might be happening with entire oceans of superheated fluids. The deeper we dig into this mystery, the more it challenges our assumptions. Even the way Neptune's atmosphere churns, with supersonic winds and colossal storms, could be redistributing heat in ways we don't fully understand. Unlike Saturn or Jupiter, where heat rises predictably, Neptune's turbulent weather might be trapping and recycling energy like a celestial pressure valve. Every new discovery peels back another layer, revealing just how dynamic and enigmatic this distant ice giant truly is. On Neptune, methane isn't just another gas, it's a potential powerhouse hiding in plain sight. While Earth's methane plays a role in trapping heat, Neptune's version might be doing something far more dramatic. The planet's vivid blue hue comes from methane absorbing red light, but beneath that striking color lies a question scientists are racing to answer. Could this simple molecule be secretly fueling Neptune's excess heat through chemical chaos? When sunlight reaches Neptune's upper atmosphere, it doesn't just bounce off, it kicks off a series of reactions that break methane apart. The process, called photodissociation, shatters methane molecules into fragments like methyl radicals and hydrogen atoms. These unstable pieces then recombine into heavier hydrocarbons like ethane and acetylene, releasing bursts of energy as they form new bonds. It's like lighting tiny invisible fires across the planet's sky, each reaction adding another drop of heat to Neptune's internal furnace. But the real intrigue lies deeper, where temperatures and pressures reach extremes we can hardly replicate on Earth. Here, methane might undergo transformations far stranger than simple breakdowns. Some theories suggest that under Neptune's crushing atmospheric pressure, methane could decompose into carbon and hydrogen, with the carbon sinking toward the core as diamond rain. Imagine glittering diamond hailstones plunging through layers of superheated fluid, each one dragging energy downward through friction, potentially heating the planet's interior like a slow-burning ember. The methane mystery doesn't stop there. Unlike Uranus, where the atmosphere appears more stagnant, Neptune's violent storms churn its gases into a continuous mixer. This constant turbulence could be dredging up fresh methane from lower layers, creating a self-sustaining cycle of destruction and rebirth. Every time a storm brings new methane to the upper atmosphere, sunlight breaks it apart anew, releasing another wave of energy. It's a planetary-scale engine, turning sunlight and gas into heat through chemistry we're only beginning to understand. Yet for all these compelling possibilities, methane alone can't account for Neptune's full thermal imbalance. The numbers still leave gaps, hinting that while atmospheric chemistry plays a role, it's likely part of a larger symphony of heat sources. From gravitational squeezing to diamond rain, Neptune seems to have mastered the art of turning ordinary processes into extraordinary energy generators. And that's what makes this ice giant not just a puzzle, but a masterclass in how little we truly know about the hidden workings of our solar system. Deep inside Neptune, where pressures reach millions of times greater than Earth's surface, something extraordinary could be happening, a perpetual storm of glittering diamonds raining down through the planet's interior. This isn't science fiction, it's a serious scientific hypothesis that might explain Neptune's mysterious heat. When methane, a molecule made of carbon and hydrogen, gets crushed under these extreme conditions, the bonds between its atoms can shatter. The freed carbon atoms, subjected to unimaginable pressures, may then crystallize into diamonds, falling like celestial gemstones toward the planet's core. But how does diamond rain generate heat? Think of it like dropping a heavy book onto a pile of pillows. The energy from the fall has to go somewhere. As these diamonds sink through Neptune's dense layers of hydrogen and helium, friction heats them up, transferring energy into the surrounding material. It's a slow but relentless process, like rubbing your hands together to warm them, except happening across thousands of miles of swirling gas. Some calculations suggest this could account for a significant portion of Neptune's unexplained thermal energy, turning what sounds like cosmic alchemy into a viable heating mechanism. What makes this theory so compelling is that we've actually recreated tiny pieces of it in labs here on Earth. Using powerful lasers or diamond anvil cells, scientists have simulated Neptune's extreme conditions, watching as methane indeed breaks apart and forms diamond-like structures. Of course, these experiments last mere nanoseconds and operate on microscopic scales. Neptune's diamond rain would be a planet-wide phenomenon occurring over billions of years. The sheer scale of this process could make it a major player in the planet's energy budget. Yet even diamond rain might not tell the whole story. For one thing, Uranus has similar atmospheric chemistry but doesn't show the same heat excess, raising questions about why Neptune's interior would behave so differently. Some researchers argue that Neptune's more active weather patterns could be churning material more efficiently, keeping the diamond cycle in constant motion. Others speculate that Neptune's core might be hotter from the start, creating conditions where sinking diamonds release even more energy through chemical reactions we haven't yet discovered. The beauty of this hypothesis lies in its ability to connect multiple mysteries: Neptune's heat, its turbulent storms, even its vivid blue color, into a single, elegant narrative. Every diamond falling through its depths could be a tiny piece of the puzzle, helping us understand not just this ice giant, but the hidden workings of planets across the galaxy. And as we push the boundaries of high-pressure physics here on Earth, we might soon find out whether this dazzling explanation holds up, or if Neptune has even stranger secrets waiting to be uncovered. Beneath Neptune's churning atmosphere, where winds howl at speeds that dwarf Earth's most violent hurricanes, lies a hidden engine that might hold the key to its unexplained heat: a molten, turbulent core. Unlike the solid iron heart of Earth, Neptune's center could be a swirling cauldron of superheated rock, encased in oceans of supersonic water and ammonia. This isn't water as we know it. Under pressures millions of times stronger than our planet's surface, these molecules break apart into bizarre, electrically conductive fluids where oxygen atoms lock into a crystalline lattice while hydrogen ions flow freely like a metallic soup. This sloshing, conductive mantle might be doing more than just existing under extreme conditions. It could be acting like a planetary scale generator. As Neptune rotates, these electrified fluids twist and churn, creating friction that heats the surrounding material. Think of it like stirring a cup of honey with a spoon, but where the honey is a searing, electrically charged fluid, and the spoon is the planet's own rotation. Every movement generates resistance, and that resistance turns into warmth, radiating outward through layers of compressed gas. But the real magic happens when you add magnetism to the mix. Neptune's lopsided, off-center magnetic field, unlike anything seen on other planets, hints at something unusual stirring deep within. On Earth, our magnetic field comes from the steady churn of molten iron in the outer core. Neptune's field, however, is tilted at a wild angle and offset from the planet's center, suggesting its dynamo isn't buried in a neat, metallic core, but might instead be churning within that conductive ocean of superionic water. If true, this could mean the very fluids that generate Neptune's magnetic shield are also contributing to its heat surplus, turning the planet's interior into a self-sustaining thermal reactor. Yet even this dazzling explanation has its gaps. For one, Uranus shares a similar composition and likely has a comparable internal structure, yet it doesn't exhibit the same heat imbalance. Why would Neptune's dynamo be so much more active? Some scientists speculate that Neptune's core might have retained more heat from its violent formation, keeping those internal fluids churning vigorously. Others point to the planet's extreme weather, which could be dredging up deeper material and stirring the pot like a cosmic spoon. Then there's the wild card, exotic chemistry. Under such extreme pressures, familiar substances like water and ammonia behave in ways that defy textbook physics. Chemical reactions we've never observed could be releasing bursts of energy as compounds form, break apart, and reform in the planet's depths. It's a reminder that Neptune isn't just a puzzle, it's a laboratory for conditions so alien, they challenge our very understanding of matter itself. The more we learn about Neptune's molten heart, the clearer it becomes that no single process can explain its heat mystery. Instead, it's likely a combination of factors: gravitational squeezing, diamond rain, atmospheric chemistry, and this sloshing dynamo, all working in concert to turn this icy giant into a thermal powerhouse. And until we can send probes deep into its atmosphere to take direct measurements, Neptune's core will remain one of the solar system's most tantalizing enigmas, whispering clues about the hidden forces that shape not just planets, but the universe itself. At first glance, Uranus and Neptune seem like nearly identical twins, both ice giants with similar sizes, compositions, and distances from the Sun. Yet when it comes to heat, they couldn't be more different. While Neptune blazes with mysterious internal energy, Uranus barely emits a whisper of excess warmth. This glaring contradiction forces us to ask, how can two planets so alike in so many ways behave so differently? The answer might lie in the subtle distinctions between them, hidden beneath their swirling atmospheres and buried in their ancient histories. Take their rotations for starters. Uranus spins nearly on its side, tipped over at a jaw-dropping 98-degree angle, as if it were rolling around the Sun like a cosmic bowling ball. This extreme tilt likely came from a cataclysmic collision early in its life, a blow so violent it may have scattered much of Uranus's primordial heat into space, leaving its interior cooler and less dynamic. Neptune, by contrast, spins upright like most planets, preserving more of that formative energy. It's the difference between a spinning top wobbling wildly and one rotating smoothly. The latter retains its momentum far longer. Then there's the matter of weather. Neptune's atmosphere is a tempest of supersonic winds and colossal storms, like the infamous Great Dark Spot, a hurricane larger than Earth. This relentless churning could be dredging up heat from deeper layers and redistributing it across the planet. Uranus, meanwhile, appears eerily calm by comparison, its atmosphere sluggish and stratified. Without that turbulent mixing, any internal warmth might stay trapped beneath layers of stagnant gas, like a pot of soup left unstirred on a stove. But perhaps the most intriguing difference lies in their cores. While both planets likely have rocky centers surrounded by exotic ices, Neptune's interior might be far more active. Some models suggest Neptune's core could still be slowly settling, with denser materials sinking toward the center and releasing gravitational energy as heat, like sand trickling through an hourglass, each grain generating a tiny burst of warmth. Uranus, on the other hand, might have already reached equilibrium, its materials having settled into stable layers billions of years ago. Even their distances from the Sun play a role. Though they orbit at roughly similar ranges, Neptune's path is slightly more elliptical, meaning its distance from the Sun varies more over time. This could create tidal forces that stretch and compress the planet's interior, generating additional heat, like flexing a wire coat hanger repeatedly until it warms in your hands. Uranus, with its more circular orbit, lacks this extra source of energy. What makes this twin mystery so compelling is how it challenges our assumptions. If two planets with nearly identical ingredients can behave so differently, what does that say about the countless ice giants orbiting distant stars? Are Uranus-like planets the norm, with Neptune as the oddball, or is our solar system hiding even deeper patterns we've yet to uncover? Every observation, every spacecraft flyby, brings us closer to understanding not just these two worlds, but the hidden rules governing planets everywhere. And that's what makes Neptune's heat more than just a curiosity. It's a key to unlocking the secrets of planetary evolution itself. When we think about heat sources in space, our minds often jump to internal forces, molten cores, gravitational friction, or radioactive decay. But what if Neptune's extra warmth comes from somewhere unexpected, like the constant bombardment of charged particles streaming from the Sun? The solar wind, a relentless torrent of electrons and protons, doesn't just create dazzling auroras, it could also deliver tiny bursts of energy to Neptune's upper atmosphere. Picture this: as those high-speed particles collide with the planet's magnetic field, they generate electrical currents that ripple through the ionosphere, creating subtle heating effects. It's like Neptune standing in a cosmic downpour where every raindrop carries a spark of warmth. The math, however, tells a different story. While solar wind interactions do contribute to Neptune's auroras, those shimmering light shows near its poles, the total energy deposited is a drop in the bucket compared to the planet's overall heat surplus. Calculations suggest this external heating accounts for less than 1% of the observed anomaly. To put it in perspective, it's like trying to heat a swimming pool with a single candle. The effect is real, but far too feeble to explain Neptune's roaring thermal imbalance. Yet dismissing solar wind entirely would be short-sighted. There's a fascinating twist here. Neptune's magnetic field isn't like Earth's neat, symmetrical bubble. It's lopsided, wobbling wildly as the planet rotates, with poles offset from its axis by nearly 47 degrees. This chaotic geometry means solar wind particles don't just glance off evenly. They slam into the magnetosphere at odd angles, creating turbulence that could amplify their heating effects in unpredictable ways. Imagine throwing pebbles into a spinning blender instead of a still pond. The chaos might scatter energy deeper than expected. Some researchers speculate this uneven interaction could churn Neptune's upper atmosphere more violently, indirectly stirring deeper layers and releasing trapped heat from below. Then there's the wild card of time. Neptune's orbit takes it through regions of varying solar wind intensity over its 165-year journey around the Sun. During periods of heightened solar activity like flares or coronal mass ejections, the planet might experience bursts of external heating that, while temporary, could leave a lasting imprint on its atmospheric dynamics. Think of it as a cosmic heat wave, fleeting but potent enough to disrupt the planet's energy balance for years afterward. The solar wind might not be the smoking gun behind Neptune's thermal mystery, but it's a reminder that planets don't exist in isolation. Every external force, no matter how small, adds another thread to the tapestry of their behavior. And as we piece together these subtle influences, we're not just solving a puzzle about Neptune, we're learning how every world, from the closest to the most distant, dances to the tune of its star. Neptune's atmosphere isn't just a layer of gas. It's a raging battlefield of storms so powerful, they make Earth's hurricanes look like breezes. The most famous of these, the Great Dark Spot, was a monstrous vortex wider than our entire planet, churning with winds that screamed at over 1,500 miles per hour. But these storms aren't just spectacular to watch. They might be key players in Neptune's heat mystery, acting like giant mixers stirring energy from the depths upward. Think of Neptune's atmosphere as a pot of boiling water on a stove. On Earth, heat rises in predictable bubbles, but Neptune's version is turbocharged. Its supersonic winds don't just move horizontally, they plunge deep, dredging up warm gases from lower layers and hurling them toward the frigid upper atmosphere. This creates a chaotic recycling system where heat isn't just radiating out. It's being violently redistributed like a cosmic blender set to max. The result: storms that don't just dissipate energy but actively shuffle it around, potentially masking how much warmth is truly coming from below. What makes this even more fascinating is how these storms differ from Jupiter's iconic bands or Saturn's hexagonal whirlpools. Neptune's weather is eerily sporadic. The Great Dark Spot, first spotted by Voyager 2 in 1989, had vanished by the time Hubble looked just 5 years later, only to be replaced by new storms in different locations. This unpredictability suggests Neptune's atmosphere isn't just releasing heat, it's generating turbulence in ways we don't fully understand. Some scientists speculate that these storms might even tap into the planet's internal energy reserves, acting like pressure valves for heat trapped far below. Then there's the wild card of chemistry. As these storms churn, they could be triggering reactions in Neptune's methane-rich atmosphere, breaking molecules apart and reforming them in ways that release bursts of energy. Imagine a storm not just as wind and rain, but as a chemical reactor where every lightning strike or atmospheric collision sparks tiny explosions of heat. This could mean Neptune's weather isn't just a side effect of its warmth, it might be an active participant in creating it. Yet for all their fury, these storms still can't account for Neptune's entire heat surplus. That's the puzzle. Even the most violent atmospheric chaos only explains part of the story. It's as if Neptune has multiple hidden furnaces, each contributing to the thermal imbalance in ways we're only beginning to unravel. And until we can peer deeper beneath those tempests, the full picture of how this icy giant stays so strangely warm will remain just out of reach. The idea of hidden oceans isn't just science fiction. We've found them on moons like Europa and Enceladus, where tidal forces from their host planets keep subsurface water liquid despite the frigid cold of space. But what about Neptune? Could this distant giant, with its fierce winds and mysterious heat, also conceal a secret sea beneath its swirling blue exterior? The possibility isn't as far-fetched as it might seem. Beneath Neptune's thick atmosphere of hydrogen, helium, and methane, scientists suspect layers of what they call hot ice water molecules forced into strange, solid states by unimaginable pressures, yet hot enough to remain semi-fluid. This slushy boundary between ice and liquid could extend hundreds of miles down, potentially giving way to a vast global ocean. Unlike the subsurface seas of icy moons, warmed by the gravitational tug of war with their planets, Neptune's hypothetical ocean would rely on a different heat source, the planet's own internal energy. The same processes that make Neptune radiate excess warmth, gravitational compression, chemical reactions, even diamond rain, might also be keeping this hidden water layer from freezing solid. There's tantalizing evidence to consider. Neptune's lopsided magnetic field, wobbling wildly as the planet rotates, hints at an electrically conductive fluid deep inside. On Earth, our magnetic field comes from molten iron, but Neptune lacks a solid metal core. Instead, that conductivity could come from a salty, mineral-rich ocean, where dissolved compounds allow currents to flow. Imagine a dark, briny sea, thicker than syrup and under pressures so intense it behaves like nothing on Earth, yet still capable of generating the chaotic magnetism we observe from afar. Then there's the chemistry. If Neptune does have a subsurface ocean, it wouldn't be pure water. Ammonia, methane, and other compounds likely mix in, lowering the freezing point and creating a bizarre, alien fluid. Some models suggest this ocean could interact with the planet's rocky core, triggering reactions that release even more heat. Picture hydrothermal vents like those on Earth's ocean floor, but scaled up to planetary proportions, spewing warmth into the surrounding abyss. But here's the twist. Unlike Europa or Enceladus, where geysers blast evidence of hidden oceans into space, Neptune's crushing gravity and thick atmosphere would trap any signs of liquid deep below. That means we can't just scan for plumes or cracks as proof. Instead, scientists rely on subtle clues, the way Neptune's magnetic field flickers, the odd distribution of heat across its surface, even the behavior of its storms. Every anomaly could be a whisper from the depths, hinting at water where we least expect it. The implications are staggering. If Neptune does harbor a subsurface ocean, it would redefine our understanding of where liquid water and potentially life could exist in the universe. Not just on moons orbiting gas giants, but within the giants themselves. And that raises a haunting question. If hidden seas can thrive in the darkness beneath Neptune's clouds, how many other planets in our solar system and beyond might be hiding similar secrets? Until we send probes brave enough to dive beneath those swirling blue storms, the answer remains as elusive as the ocean itself. Deep inside Neptune's core, where pressures crush atoms into configurations never seen on Earth, ordinary rules of physics might not apply. This isn't just about extreme conditions, it's about matter behaving in ways that defy textbooks. Scientists suspect Neptune's interior could harbor exotic substances like metallic hydrogen, where the lightest element in the universe transforms into a shimmering, conductive metal under millions of atmospheres of pressure. Or superionic ice, a bizarre form of water where oxygen atoms lock into a rigid lattice while hydrogen ions flow through it like a liquid, creating a material that's both solid and fluid at the same time. These aren't just curiosities, they could be the missing pieces in Neptune's heat puzzle. Take metallic hydrogen, for instance. On Jupiter, where pressures are even more extreme, this material is thought to generate powerful magnetic fields. But on Neptune, where pressures are slightly lower, hydrogen might exist in a slushy, partially metallic state, creating friction as it swirls against other layers. Imagine stirring a vat of molten metal. The resistance generates heat, and on Neptune, that process could be happening across thousands of miles of compressed gas. Even more intriguing is the possibility that this metallic hydrogen isn't uniform. It might form pockets or veins, creating localized hotspots where energy builds up and leaks into the surrounding atmosphere. Then there's supersonic ice. Unlike the ice in your freezer, this variety doesn't melt when heated, it just gets weirder. Under Neptune's crushing pressures, the hydrogen ions breaking free from their oxygen cages could carry electric currents, contributing to the planet's lopsided magnetic field while also releasing heat through ionic motion. Picture a grid of oxygen atoms vibrating as hydrogen ions zip between them, each collision releasing a tiny burst of energy. Multiply that by the volume of an entire planetary mantle, and you've got a potential furnace hidden beneath the clouds. But the real wild card, matter we haven't even discovered yet. At these extreme pressures and temperatures, familiar elements might bond in ways we've never observed. Some theories suggest compounds like magnesium oxide or silica could dissolve into Neptune's fluid layers, forming dense, heat-generating soups that sink toward the core. Others speculate about dark hydrogen, a hypothetical state where hydrogen molecules break down into a dense, conductive fog that radiates warmth as it circulates. What makes these ideas so compelling is how they challenge our understanding of planetary interiors. Neptune isn't just a gas giant, it's a laboratory for states of matter that can't exist anywhere else. And if even one of these exotic materials is lurking beneath its storms, it could rewrite the rules of planetary science. Until we can probe deeper, either with advanced telescopes or a daring atmospheric mission, these possibilities remain tantalizing glimpses into a world where physics as we know it is just the beginning. Neptune's 28-degree tilt might seem modest compared to Uranus's sideways spin, but this subtle wobble could be quietly fueling the planet's mysterious heat. Unlike Earth's stable 23.5-degree tilt, Neptune's axial lean creates seasons so extreme they reshape entire hemispheres over decades. As the planet orbits the Sun over its 165-year journey, each pole tilts toward the sunlight for stretches lasting 40 Earth years, long enough to bake one side while the other plunges into prolonged darkness. But here's the twist: seasonal changes aren't just about surface temperature. They might be stirring Neptune's interior like a slow-motion mixer, driving currents that generate friction and heat deep below the clouds. The key lies in how Neptune's tilt affects its atmospheric circulation. When a pole faces the Sun, intense heating creates colossal storms and supersonic winds that don't just skim the upper atmosphere, they plunge downward, dragging energy into the planet's depths. Imagine dropping a stone into a pond, but instead of ripples, the impact sends shockwaves through the entire planet. These turbulent motions could churn Neptune's fluid interior, creating eddies and currents that convert kinetic energy into warmth. It's like shaking a snow globe where every swirling motion releases tiny bursts of heat from friction. Yet the real intrigue comes from Neptune's lopsided magnetic field, which amplifies this effect. Unlike Earth's relatively orderly magnetosphere, Neptune's field is chaotic, tilted 47 degrees from its axis and offset from the planet's center. This asymmetry means seasonal changes don't just alter weather patterns, they tug at the magnetic field itself, generating electrical currents in the conductive layers below. Those currents could act like invisible heating coils, warming the surrounding material through electromagnetic friction. Picture rubbing a balloon against your hair to create static, but scaled up to planetary proportions, with entire oceans of ionized fluid crackling with energy. But there's a catch. Uranus shares a similar tilt and seasonal cycle, yet it lacks Neptune's dramatic heat surplus. Why would wobble-driven heating work on one ice giant and not the other? The answer might lie in Neptune's more dynamic interior. While Uranus's core appears relatively stagnant, Neptune's churning layers could be amplifying seasonal effects, turning small orbital nudges into significant thermal output. Think of it like pushing a child on a swing. Give the right timing, and tiny pushes build into big arcs. Neptune's internal turbulence might be doing the same, resonating with seasonal changes to produce outsized heating. The deeper we dig into this theory, the more it blurs the line between external and internal forces. Neptune's tilt isn't just a quirk of its orbit. It could be a hidden engine, transforming sunlight and gravity into the very heat that defies explanation. And if that's true, it suggests a universe where even a planet's wobble can shape its destiny, turning celestial mechanics into a cosmic power source. Neptune's largest moon, Triton, doesn't just orbit the planet, it defies convention in spectacular fashion. While most moons circle their planets in the same direction as their rotation, Triton spins backward, a cosmic rebel hurtling through space the wrong way. This retrograde orbit isn't just a quirk, it's a clue that Triton wasn't born alongside Neptune but was likely captured from the Kuiper belt, pulled into orbit by the planet's immense gravity. And that violent past might still be shaping Neptune today, as Triton's backward dance creates tidal forces that could be heating the planet from the outside in. Tidal heating works like this. As Triton orbits, Neptune's gravity stretches and squeezes the moon, generating friction inside its icy shell. But the reverse is also true. Triton's gravity tugs back on Neptune, ever so slightly distorting its shape. Every time Triton completes a loop, this gravitational push and pull flexes Neptune's interior like kneading dough. That constant flexing converts energy into heat, warming the planet's depths through a process called tidal dissipation. On a moon like Jupiter's Io, tidal heating is so extreme it fuels volcanic eruptions. Neptune's version would be far gentler, but over billions of years, even a whisper of extra warmth could add up. The question is how much. Calculations suggest Triton's tidal influence is subtle, perhaps contributing just 1% of Neptune's total heat surplus. That might sound insignificant, but in planetary terms, even a trickle matters. Imagine leaving a single light bulb on in a massive warehouse. Alone, it's barely noticeable, but combined with other small heat sources like residual formation energy, gravitational compression, or diamond rain, it helps tip the scales. What makes this particularly fascinating is how Triton's influence might vary over time. When Neptune first captured the moon, their gravitational tango would have been far more intense, generating enough heat to potentially reshape both worlds. As Triton's orbit stabilized, the effect diminished, but it never fully vanished. Today, the moon's slow spiral toward Neptune, destined to one day be torn apart by tidal forces, means the heating could be increasing again. A slow crescendo in a cosmic symphony that won't reach its climax for billions of years. Yet even this elegant explanation has its limits. Uranus, which lacks a massive, close-orbiting moon like Triton, should theoretically have weaker tidal heating, yet Neptune's heat excess remains far more pronounced. This discrepancy hints that while Triton's tides might nudge the needle, they're not the sole driver of Neptune's warmth. Instead, they're part of a complex interplay of forces, each contributing a small piece to a puzzle we're still assembling. And that's the beauty of studying Neptune. Every answer uncovers new questions, reminding us that even in our own solar system, the simplest phenomena can hide layers of mystery. At first glance, Neptune seems nothing like a star. It's a frigid, storm-racked world with no visible glow. But what if this icy giant was once on the path to stardom, only to fall short? This is the essence of the failed star theory, which suggests Neptune might have been a brown dwarf in the making, a cosmic almost winner that never quite gathered enough mass to ignite nuclear fusion. Brown dwarfs, often called stars that couldn't, are celestial oddballs too massive to be planets but too small to sustain the hydrogen fusion that powers true stars. Instead, they smolder faintly, radiating leftover heat from their formation. Could Neptune be hiding similar processes beneath its swirling blue clouds? The math, however, quickly complicates this idea. For an object to qualify as a brown dwarf, it needs at least 13 times Jupiter's mass, enough to briefly fuse deuterium, a heavy isotope of hydrogen. Neptune clocks in at just 17 times Earth's mass, making it far too lightweight to even flirt with stellar ambitions. To put that in perspective, you'd need to stack over 20 Neptunes together to reach the threshold for deuterium burning. Even then, the heat from such reactions would be minuscule compared to what we observe. Brown dwarfs cool dramatically over time, and after billions of years, their residual warmth wouldn't come close to Neptune's current output. But here's where the theory takes an interesting turn. While Neptune itself isn't a brown dwarf, some researchers speculate it could contain materials more commonly found in these stellar misfits. Elements like lithium or deuterium, which play key roles in brown dwarf chemistry, might exist in trace amounts within Neptune's depths. Under extreme pressures, these elements could undergo rare nuclear reactions, releasing pockets of heat, not enough to light up a star, but perhaps enough to contribute to the planet's thermal surplus. Imagine a handful of glowing embers buried in a snowbank. They wouldn't melt the whole drift, but they'd create localized warmth. The catch: no mission has ever detected the telltale signatures of such reactions on Neptune. Without direct evidence of unusual isotopes or radiation, the failed star idea remains speculative at best. Even if these processes are occurring, they'd likely be a minor footnote in Neptune's heat budget, not the primary driver. That said, the theory isn't entirely without merit. It challenges us to think creatively about how planetary and stellar boundaries blur, especially in the murky realm of ice giants and substellar objects. What makes this hypothesis so compelling isn't its accuracy, but the questions it raises. If Neptune isn't a brown dwarf, why does it share some traits with them, like turbulent atmospheres and complex magnetic fields? Could there be a spectrum of objects bridging the gap between planets and stars, with Neptune hovering at one end? As we discover more exoplanets, some with masses and orbits that defy classification, the line between planet and failed star grows fuzzier. Neptune might not be a dim stellar wannabe, but it's certainly teaching us how much we still have to learn about the twilight zone where giants roam. Neptune might not be generating heat at all. It could simply be holding onto it with cosmic stubbornness. Unlike Earth, where heat escapes relatively quickly through volcanoes, earthquakes, and plate tectonics, Neptune's icy composition acts like a colossal thermos, trapping warmth from its violent birth and letting it seep out at an achingly slow pace. This concept, called thermal inertia, suggests the planet isn't producing excess energy. It's just exceptionally good at conserving what it started with billions of years ago. Picture a cast iron skillet pulled from the oven. Even after hours, it's still warm to the touch. Now imagine that skillet is a planet 300 times Earth's mass, and you've got a sense of how Neptune might be hoarding its heat. The secret lies in Neptune's layered interior. Beneath its turbulent atmosphere, the planet isn't just a uniform ball of gas. It's a tiered structure of slushy ices, superheated fluids, and rock, each with different insulating properties. Water, ammonia, and methane ices dominate the outer mantle, but under Neptune's crushing pressures, these familiar substances behave unlike anything on Earth. They form dense, viscous layers that conduct heat poorly, creating a natural barrier that slows the escape of internal warmth. It's like wrapping the planet in a blanket of cosmic insulation, where energy takes eons to work its way to the surface. Then there's the matter of convection, or rather, the lack of it. On Earth, heat rises efficiently through molten rock and shifting tectonic plates. Neptune, by contrast, lacks a solid surface to break up its fluid layers into efficient heat-transferring cells. Instead, its interior likely churns in sluggish, globe-spanning currents, with warm material taking millions of years to circulate from core to cloud tops. Some models suggest that Neptune's deepest heat might not have even reached the surface yet, still inching upward through layers of exotic matter like supersonic ice. But here's the twist: thermal inertia alone can't fully explain Neptune's heat imbalance. If the planet were just slowly cooling, its twin Uranus, with nearly identical size and composition, should behave similarly. Yet Uranus radiates barely any excess warmth, suggesting Neptune's heat retention is only part of the story. This discrepancy points to something more dynamic at play. Perhaps Neptune started with a hotter core, or its turbulent weather is dredging up buried energy faster than it can dissipate. Even the planet's tilt and magnetic field might be working together to redistribute heat in ways we haven't yet unraveled. The beauty of this theory is how it connects to the broader universe. If Neptune's heat is largely primordial, it offers a glimpse into the frenzied conditions of the early solar system, when planets were little more than coalescing balls of molten debris. Every joule of warmth radiating from Neptune today could be a whisper from that ancient era, a reminder of how planetary interiors hold onto their past far longer than their surfaces suggest. And as we study ice giants in distant star systems, this slow-cooking phenomenon might prove to be the rule rather than the exception, a cosmic lesson in patience written in the language of fading heat. Peering through telescopes from billions of miles away can only tell us so much about Neptune's secrets. To truly crack the case of its mysterious heat, we need to go there, to plunge through those swirling blue clouds and study the planet up close. That's where future missions come in, armed with cutting-edge technology designed to brave Neptune's extreme environment and send back data that could rewrite planetary science. One of the most promising proposals is NASA's Triton, a daring flyby mission designed to map Neptune's magnetic field in unprecedented detail while scanning its moon Triton for clues. Unlike Voyager 2's fleeting visit in 1989, Triton would carry instruments capable of detecting subtle gravitational tugs and heat signatures hidden beneath the planet's atmosphere. Imagine it as a cosmic metal detector, revealing the invisible forces churning beneath Neptune's surface. But the real game-changer might be its focus on Triton. By studying how this captured moon interacts with Neptune's gravity and magnetic field, scientists could uncover hidden tides or internal motions contributing to the planet's warmth. Then there's the Dream mission, a dedicated Neptune orbiter. Picture a spacecraft circling the ice giant for years, tracking storms, measuring atmospheric chemistry, and even deploying probes to dive beneath the clouds. These probes could analyze pressure and temperature gradients at different depths, pinpointing exactly where Neptune's excess heat originates. Some concepts even include seismometers to detect Neptune quakes, vibrations echoing through the planet's interior that could reveal the structure of its core. It's like giving the planet an X-ray, exposing the hidden engines driving its thermal imbalance. But getting there won't be easy. Neptune's distance makes communication slow, and its faint sunlight limits solar power options. Future missions might rely on advanced nuclear batteries or innovative propulsion systems to shorten the decade-long journey. The payoff, though, would be immense. Beyond solving the heat mystery, these missions could uncover whether Neptune harbors subsurface oceans, how its diamond rain behaves, or even if exotic states of matter truly exist in its depths. The clock is ticking. With every passing year, Neptune's storms shift, its heat ebbs, and clues fade into the cosmic background noise. But with missions like Triton on the horizon, we might finally be on the verge of unraveling one of the solar system's last great planetary enigmas. And when we do, the answers could redefine not just how we see Neptune, but how we understand every ice giant spinning in the darkness beyond our sun. To unlock Neptune's secrets, scientists don't need to travel billions of miles. They're recreating the planet's extreme conditions right here on Earth. Inside specialized labs around the world, researchers use tools like diamond anvil cells and high-powered lasers to simulate the crushing pressures and scorching temperatures found deep within Neptune's interior. These aren't just scaled-down experiments, they're windows into a realm where matter behaves in ways that defy everyday logic. Take the diamond anvil cell, a device no bigger than a coffee mug but capable of replicating pressures over 1,000,000 times Earth's atmosphere. By squeezing tiny samples between two flawless diamonds, the hardest known material scientists can watch as ordinary substances transform. Water turns into supersonic ice, methane fractures into diamond rain, and hydrogen morphs into a shimmering metal. These experiments aren't just theoretical. In 2020, a team at Stanford observed methane breaking down into diamonds under Neptune-like conditions, confirming a decades-old hypothesis. The process releases energy, offering a plausible clue to the planet's heat surplus, like watching cosmic alchemy in real time. Then there are the lasers. Facilities like the National Ignition Facility in California use pulses of light more powerful than the entire U.S. electrical grid, if only for a fraction of a second, to blast materials with temperatures rivaling Neptune's core. In these fleeting moments, gases compress to densities never seen on Earth, revealing how heat might propagate through the planet's slushy mantle. One groundbreaking study showed that under such extremes, mixtures of water and ammonia form strange, conductive fluids, exactly the sort of material that could explain Neptune's lopsided magnetic field. But the real magic happens when these experiments collide with supercomputers. By feeding lab data into advanced simulations, researchers can extrapolate how these microscale reactions play out across a planet 15 times Earth's mass. The results are startling. Some models suggest Neptune's interior might be layered like a cosmic onion, with each stratum, from the diamond-rich mantle to the supersonic ocean, contributing its own unique heat signature. Other simulations hint at turbulence we've never observed, where storms dredge up heat from the core and redistribute it through the atmosphere in chaotic waves. What makes this work so revolutionary isn't just the discoveries themselves, but how they reshape our understanding of planetary science. Every time a lab recreates a slice of Neptune's environment, it's like decoding a piece of extraterrestrial physics right here at home. And as these experiments grow more sophisticated, pushing pressures higher, durations longer, and measurements finer, we inch closer to solving the ultimate riddle: how a world so far from the sun burns so fiercely from within. Neptune's magnetic field isn't just unusual, it's downright chaotic. While Earth's magnetic field lines up neatly with its rotation axis, Neptune's is tilted at a jaw-dropping 47 degrees and offset from the planet's center by nearly half its radius. This lopsided, wobbly magnetosphere looks less like a structured shield and more like a cosmic toddler's first attempt at drawing a spiral. But this disorder might be more than just a curiosity. It could be a hidden engine churning out heat deep within the planet's interior. The key lies in how Neptune's magnetic field interacts with its fluid layers. Unlike Earth, where the field is generated by molten iron swirling in the outer core, Neptune's dynamo likely operates in a vast ocean of electrically conductive material. Think supersonic water or metallic hydrogen. As the planet rotates, this sloshing, conductive fluid twists the magnetic field into its bizarre configuration, creating friction that converts motion into heat. Imagine stirring a pot of thick soup with a spoon. The resistance warms the liquid slightly. Now scale that up to a planetary level, where the spoon is Neptune's rotation, and the soup is an entire ocean of exotic, charged fluid. The result, a slow but steady release of thermal energy that could explain part of the planet's unexplained warmth. What makes this even more intriguing is the field's instability. Neptune's magnetic poles aren't fixed. They wander erratically, sometimes flipping positions entirely over geological timescales. This constant shuffling means the dynamo is far more turbulent than Earth's, potentially amplifying heat production. Some models suggest these chaotic motions could generate localized hotspots where energy concentrates, like invisible bonfires buried beneath the clouds. Yet there's a catch. Uranus, with its similarly tilted and offset magnetic field, doesn't exhibit the same heat excess. Why would Neptune's field produce more warmth? The answer might lie in the planet's deeper internal motions. Neptune's more active weather and atmospheric turbulence could be stirring its conductive layers more vigorously, turning the magnetic field into a more efficient heat generator. It's the difference between gently swirling a cup of tea and shaking it violently. The latter releases far more energy. The implications stretch beyond our solar system. If Neptune's wonky magnetic field truly contributes to its heat, similar processes could be at work on exoplanets orbiting distant stars. These icy giants might hide their own turbulent dynamos, silently radiating warmth into the void. And with missions like the proposed Neptune Odyssey aiming to map the planet's magnetic field in unprecedented detail, we might soon have the data to confirm whether this cosmic generator is real, or if Neptune's heat has even stranger origins waiting to be uncovered. Peering into Neptune's hidden warmth requires more than just visible light. It demands eyes that can see the invisible. That's where infrared telescopes like the James Webb Space Telescope come in, acting as cosmic thermometers tuned to the heat radiating from this distant ice giant. Unlike optical telescopes that capture Neptune's iconic blue hues, JWST infrared sensors detect the faint glow of thermal energy escaping through its atmosphere, painting a vivid picture of the planet's internal furnace. Every wavelength of infrared light tells a story, revealing not just how much heat Neptune emits, but where it's coming from deep within those churning clouds. The magic lies in the details. As Neptune's heat rises from its interior, different gases in its atmosphere absorb and re-emit infrared radiation at unique wavelengths. Methane, for instance, leaves a distinct fingerprint around 3.3 micrometers, while hydrocarbons like ethane glow brighter at longer wavelengths. JWST-sensitive instruments can separate these signals like a prism splitting light, allowing scientists to map the planet's thermal structure layer by layer. Imagine listening to an orchestra and picking out individual instruments. The violin's high notes might represent upper atmospheric heating, while the deep cello tones trace warmth surging from the core. These observations have already upended expectations. Early JWST data revealed that Neptune's south pole is significantly warmer than predicted, with temperatures soaring higher than anywhere else on the planet. This unexpected hotspot suggests active processes, perhaps atmospheric compression or chemical reactions pumping heat upward in a concentrated plume. Even more intriguing are the variations between Neptune's equatorial and polar regions, which don't match standard models of heat distribution. It's as if the planet has invisible thermal highways, funneling energy in ways we're only beginning to decipher. But infrared astronomy isn't just about snapshots. By observing Neptune over time, telescopes like JWST can track how its heat fluctuates with seasons or storm activity. When massive vortices like the Great Dark Spot churn through the atmosphere, they leave behind thermal wakes, subtle shifts in infrared glow that hint at how deep these storms reach. Some disturbances appear to dredge up warmth from hundreds of miles below, like a spoon stirring hot syrup from the bottom of a pot. These dynamic patterns suggest Neptune's heat isn't just leaking out passively, it's being actively redistributed by atmospheric chaos. The real power of these observations lies in their ability to test theories. Does the data match predictions from diamond rain models? Are there signs of tidal heating or residual formation energy? By comparing JWST infrared maps with laboratory simulations and supercomputer models, scientists can rule out some explanations while elevating others. For instance, if the heat distribution aligns with predictions for gravitational compression, that process moves up the list of likely culprits. If certain wavelengths reveal unexpected chemical byproducts, it could point to methane breakdown or exotic material interactions. Yet for all their precision, infrared measurements still leave gaps. Neptune's upper atmosphere can mask deeper thermal signals, like fog obscuring a landscape. Future missions might combine JWST bird's eye view with probes descending through the clouds, offering ground truth data to refine the models. Until then, every photon of infrared light captured from 4 billion kilometers away brings us closer to solving the riddle of why this icy realm burns so brightly against the cold dark of space. Helium might seem like a passive bystander in Neptune's chaotic atmosphere, but this lightweight element could be playing a far more dramatic role than we've ever imagined. Deep within the planet's churning layers, where pressures reach millions of times greater than Earth's surface, helium doesn't just mix harmlessly with hydrogen, it separates out, forming droplets that rain downward like a slow-motion celestial drizzle. This process, known as helium precipitation, isn't just a curiosity. It could be releasing latent heat as those droplets sink, adding another piece to Neptune's thermal puzzle. Think of it like this: when helium condenses into droplets and begins its long descent, it's not just falling, it's exchanging energy with its surroundings. Every collision with hydrogen molecules transfers a tiny burst of warmth, like rubbing your hands together on a cold day. Multiply that by trillions of droplets cascading through thousands of miles of dense atmosphere, and suddenly, this gentle rain becomes a significant heat source. The deeper the helium sinks, the more extreme the pressures grow, squeezing those droplets until they dissolve back into the surrounding soup, releasing even more energy in the process. It's a cycle as relentless as it is subtle, quietly pumping heat into Neptune's interior over billions of years. But here's where it gets fascinating. Helium rain isn't uniform. It likely happens in patches or layers, creating invisible rivers of energy flowing through the planet's depths. Some models suggest these helium-rich zones could act like thermal highways, channeling warmth toward Neptune's core or redistributing it through turbulent eddies. Imagine a pot of simmering water with pockets of oil bubbling up. The uneven densities create motion, stirring the pot without a spoon. On Neptune, that unevenness might come from helium's tendency to clump and separate, driving convection in ways we're only beginning to understand. Yet for all its potential, helium rain faces a major hurdle: Uranus. If this process were the primary driver of Neptune's heat, why doesn't its icy twin show the same thermal excess? Both planets have similar compositions, with hydrogen and helium dominating their atmospheres. The answer might lie in Neptune's more active interior. Its stronger gravitational compression and turbulent weather could be churning helium more efficiently, keeping the precipitation cycle in overdrive. Alternatively, Neptune might simply have started with more helium in its deeper layers, giving it a larger reservoir to tap into. The wild card here is how helium behaves under Neptune's extreme conditions. In labs, scientists have used diamond anvil cells to simulate the planet's interior, watching as helium morphs from a gas into a strange, liquid-like state under pressure. These experiments hint that helium might not just rain down. It could form exotic compounds with hydrogen or other elements, releasing bursts of energy through chemical reactions we've never observed on Earth. What makes this theory so compelling is its elegance. Helium rain doesn't require dramatic new physics or unseen materials. It relies on subtle interactions between the planet's most abundant elements. And if proven, it would mean Neptune's warmth isn't just coming from one or two grand sources, but from countless tiny contributions, each droplet a whisper in the chorus of the planet's hidden heat. As we peer deeper into Neptune's secrets, it's becoming clear that even the quietest players, like helium, might have starring roles in the story of why this icy giant burns so brightly against the void. Neptune's heat isn't just a mystery, it's a ticking clock. If this ice giant is running on leftover warmth from its violent birth 4.5 billion years ago, that energy should be fading by now, slowly leaking into the frozen depths of space. But here's the puzzle. Current measurements show Neptune radiating 2.5 times more heat than it receives from the Sun, a surplus that defies simple cooling models. To understand why, we need to play cosmic detective, piecing together how long primordial heat can last and whether Neptune's output makes sense for its age. Start with the basics. When planets form, they're born hot molten balls of rock, ice, and gas forged from countless collisions. Over time, that heat escapes through radiation and convection, cooling the planet like a steaming cup of coffee left on a counter. For rocky worlds like Earth, this process is relatively straightforward. Heat escapes through volcanic activity and plate tectonics. But gas and ice giants like Neptune are different. Their thick, fluid layers act like insulation, slowing the loss of internal warmth to a crawl. The question isn't just whether Neptune is cooling, it's whether it's cooling fast enough to explain its current heat output. Crunching the numbers reveals a discrepancy. If Neptune were simply radiating leftover formation energy, models suggest its heat should have dropped by roughly half over the last 4 billion years. Yet the planet's current emission rates are far higher than those projections, as if someone turned the thermostat up when we weren't looking. This gap hints that Neptune isn't just passively cooling, it's actively generating heat through processes we're only beginning to understand. One clue comes from comparing Neptune to its siblings. Jupiter and Saturn also radiate excess heat, but their massive sizes mean they can retain primordial warmth far longer. Neptune, smaller and farther from the Sun, should have cooled more dramatically by now. Even stranger, Uranus-Neptune's near twin in size and composition barely emits any excess heat at all. If both planets formed under similar conditions, why is one still glowing while the other has nearly gone dark? This mismatch suggests Neptune's heat isn't just a relic of its birth but something more dynamic, a combination of residual energy and ongoing internal activity. The answer might lie in Neptune's interior dynamics. Unlike Uranus, which appears geologically stagnant, Neptune's churning atmosphere and turbulent weather could be dredging up deep-seated warmth, redistributing it like a cosmic conveyor belt. Gravitational compression, where the planet's own weight squeezes its core, might also be generating fresh heat, counteracting the gradual cooling. Then there's the wild card of chemistry, exotic reactions in Neptune's high-pressure mantle, like diamond rain or helium precipitation, releasing energy as materials transform under extreme conditions. But the most intriguing possibility, Neptune's heat isn't just old, it's renewable. Seasonal shifts, tidal forces from its moon Triton, or even interactions with the solar wind could be adding subtle but continuous energy to the system, like a slow recharge to an ancient battery. Whatever the case, this icy giant is teaching us that planetary cooling isn't a one-size-fits-all process. Some worlds hold onto their youth far longer than expected, and Neptune, it seems, is determined to keep its fires burning against the cold of deep space. What if Neptune's heat isn't just a planetary quirk, but a cosmic clue pointing to forces beyond our current understanding? Some scientists are daring to ask whether dark matter, the invisible scaffolding of the universe, could be silently fueling Neptune's furnace. The math is speculative but tantalizing. If dark matter particles occasionally collide with regular matter in Neptune's core, those rare interactions might release bursts of energy. Picture a game of pool where most balls glide unseen except for the occasional strike that sends a visible ball careening. On Neptune, those strikes could translate to heat, with dark matter acting like ghostly pool cues nudging atoms into motion. Then there's quantum mechanics, where the rules get even stranger. Under extreme pressures, Neptune's interior might host phenomena like quantum friction, where particles at atomic scales generate heat through sheer proximity. Normally, this effect is too weak to notice, but compressed into Neptune's dense mantle, it could add up. Think of it like the static cling between socks fresh from a dryer, but scaled to planetary proportions, with trillions of atomic interactions creating a faint but measurable warmth. Even more radical is the idea of primordial black holes. These hypothetical relics from the Big Bang, no larger than a grapefruit but as massive as a mountain, could theoretically lurk in Neptune's core. As they slowly evaporate via Hawking radiation, they'd emit energy like a dying ember in a cosmic campfire. While no evidence supports this yet, it's a reminder of how far our imagination must stretch to explain the universe's oddities. But perhaps the wildest theory involves neutrino interactions. These nearly massless particles, streaming through the cosmos by the trillions every second, usually pass through planets like ghosts. Yet some models suggest that in Neptune's ultra-dense interior, neutrinos might occasionally scatter off atomic nuclei, depositing traces of energy. Over billions of years, even these vanishingly rare events could contribute to the planet's heat surplus. It's like counting on a single raindrop to fill a bucket, except the bucket is Neptune and the drops never stop falling. These ideas aren't mainstream yet. They live on the edge of astrophysics, where creativity dances with calculation. But that's how science progresses, by daring to ask, what if, until the improbable becomes plausible. Neptune, with its defiant warmth, might just be the perfect laboratory to test the limits of our cosmic imagination. Among the swirling theories about Neptune's heat, some stray far from scientific reality, like the idea that advanced alien civilizations are secretly warming the planet. While it's fun to imagine hidden reactors or extraterrestrial engineering beneath those blue clouds, the truth is far more fascinating than fiction. Let's tackle these myths head-on, not with dismissal, but with the sheer weight of evidence that paints a clearer, if no less mysterious, picture of what's really happening. First, the notion of artificial heat sources crumbles under basic physics. For an external force, alien or otherwise, to generate Neptune's thermal surplus, it would require energy outputs comparable to a small star. Such a colossal footprint would be impossible to hide. our telescopes would detect unnatural radiation patterns or irregularities in the planet's magnetic field. Instead, every measurement aligns with natural processes, from the predictable decay of radioactive elements to the rhythmic pulses of gravitational compression. Even Neptune's lopsided magnetic field, often cited as proof of tampering, fits neatly into models of turbulent fluid dynamics in its interior. Then there's the myth that Neptune's heat is unique in the solar system, a fluke that defies explanation. In reality, gas and ice giants have been radiating excess energy since their discovery. Jupiter emits nearly twice the heat it receives from the Sun, while Saturn's output is even more extreme. Neptune's warmth isn't an anomaly, it's part of a spectrum that scientists have studied for decades. The real puzzle isn't whether the heat exists, but why Neptune's output so drastically outpaces its twin, Uranus. That discrepancy points to planetary science, not cosmic conspiracy. Another popular misconception suggests Neptune's storms are artificially sustained, as if some unseen hand is stirring the pot. But atmospheric modeling reveals a simpler truth. The planet's supersonic winds and colossal vortices arise from fundamental fluid dynamics, amplified by Neptune's rapid rotation and lack of a solid surface. The Great Dark Spot wasn't a manufactured phenomenon, it was a natural tempest born from the same chaotic energy that drives hurricanes on Earth, just scaled to monstrous proportions. Perhaps the most persistent myth is that Neptune's heat signals ongoing geological activity, like volcanoes or tectonic plates. While these processes explain warmth on rocky worlds, ice giants operate differently. Neptune's energy comes from its fluid interior, where friction, compression, and chemical reactions replace molten lava and shifting crusts. The absence of surface eruptions doesn't mean the planet is dormant. It means we need to expand our definition of what active looks like on a world without solid ground. Dispelling these myths isn't about crushing imagination. It's about redirecting wonder toward the genuine marvels Neptune holds. The planet doesn't need alien technology to be extraordinary. Its very existence challenges our understanding of physics, chemistry, and planetary evolution. Every storm, every flicker of excess heat is a natural laboratory for phenomena we're only beginning to comprehend. And that's the real magic. The universe, left to its own devices, is stranger than any fiction we could invent. To peer into Neptune's future, scientists don't need a time machine. They've got something almost as powerful: supercomputers capable of crunching billions of calculations per second. These digital crystal balls simulate Neptune's thermal evolution, modeling how its heat might wax or wane over epochs. The process starts with the present feeding in every scrap of data we have, from Voyager 2's fleeting flyby to James Webb's infrared snapshots. Then the algorithms kick in, accounting for everything from gravitational compression to atmospheric chemistry, even the slow decay of radioactive elements buried deep in the core. The result, a glimpse of how this icy giant could transform over millions or even billions of years. One startling revelation from these simulations is just how resilient Neptune's heat might be. Unlike rocky planets that cool rapidly, Neptune's fluid layers act like a thermal battery, releasing energy at a glacial pace. Some models suggest its current heat surplus could persist for another 2 to 3 billion years, long after Earth's oceans have boiled away under the sun's growing intensity. But the real surprise comes when researchers tweak the variables, adjust Neptune's internal composition slightly, say, increasing the proportion of methane or helium, and the planet's thermal output swings dramatically. It's a reminder that small differences in chemistry can have planetary-scale consequences. Then there's the wild card of Triton's tidal influence. As Neptune's largest moon spirals closer over eons, its gravitational tug will grow stronger, potentially injecting fresh heat into the planet's interior. Simulations show this process accelerating as Triton nears its doom, creating a late-stage thermal spike before the moon finally tears apart. Imagine a dying star flaring up one last time. Neptune might experience a similar burst of warmth, a final defiant glow before the long cooling begins. But not all models agree. Some predict a slower, steadier decline, with Neptune's heat bleeding into space almost imperceptibly. Others hint at cyclical patterns, where periods of intense storm activity dredge up buried warmth, creating temporary spikes in thermal output. The discrepancies reveal just how much we still don't know, especially about the behavior of exotic materials under Neptune's extreme conditions. Without direct measurements from its interior, even our most advanced simulations remain educated guesses wrapped in layers of uncertainty. What makes these projections so valuable isn't just their insight into Neptune, it's how they refine our understanding of exoplanets. Thousands of ice giants orbit distant stars, and many likely share Neptune's mysterious warmth. By decoding the mechanisms driving one, we unlock clues to countless others. Every simulation, every tweaked variable brings us closer to answering the ultimate question: is Neptune's heat a cosmic anomaly or a hidden rule waiting to be uncovered? Until we send probes beneath those blue clouds, supercomputers offer our best window into the future of this enigmatic world and the countless others like it. Neptune isn't just a puzzle in our own solar system, it's a Rosetta Stone for deciphering the thousands of icy giants orbiting distant stars. As astronomers discover more exoplanets, many bear striking resemblances to Neptune, similar sizes, compositions, and orbits far from their host stars. But here's the catch: without understanding how Neptune generates its mysterious heat, we're left guessing whether these distant cousins could harbor hidden oceans, turbulent weather, or even conditions ripe for life. Take the class of planets nicknamed mini-Neptunes, worlds slightly smaller than our ice giant but shrouded in thick hydrogen-rich atmospheres. Some orbit in the habitable zones of their stars, where temperatures might allow liquid water if they have the right internal dynamics. Neptune's heat teaches us that these exoplanets could be far more geologically active than their frigid surfaces suggest. A planet like K218b, for example, might hide a subsurface ocean kept liquid not by starlight alone, but by tidal forces or internal heating mimicking Neptune's own furnace. The implications are staggering. What we've dismissed as frozen wastelands could be shrouded nurseries for chemistry we've yet to imagine. Then there's the role of magnetic fields. Neptune's lopsided magnetosphere, chaotic yet powerful, suggests ice giants might generate protective shields differently than rocky worlds. For exoplanets bombarded by harsh stellar radiation, a Neptune-like magnetic field could mean the difference between a stripped atmosphere and a stable environment. Imagine a distant ice giant with a wobbling magnetic pole, its auroras painting the sky while shielding subterranean seas, a haven for life in an otherwise hostile cosmos. But the most profound lesson lies in diversity. Neptune and Uranus, nearly twins in size and composition, couldn't be more different thermally. This tells us that two planets formed from the same materials under similar conditions can evolve radically distinct personalities. Apply that to exoplanets, and suddenly every ice giant becomes a wild card. One might be a dormant frozen orb, while its neighbor, identical in size and orbit, could churn with hidden energy, all because of subtle differences in formation history, moon interactions, or internal chemistry. The search for life has long focused on Earth-like worlds, but Neptune's enigma forces us to broaden our horizons. If a planet so distant from its star can sustain dynamic processes for billions of years, what other possibilities await in the darkness? The answers won't just reshape how we see ice giants, they'll redefine where and how we look for life in the universe. Solving Neptune's heat mystery isn't a solo mission. It's a global collaboration, with scientists across continents pooling expertise, technology, and curiosity to crack this cosmic enigma. From observatories perched on remote mountaintops to supercomputers humming in research labs, the effort to understand Neptune's warmth stretches far beyond any single institution or nation. Take the James Webb Space Telescope, a marvel of engineering operated by NASA, the European Space Agency, and the Canadian Space Agency. Its infrared eyes, trained on Neptune from 1,000,000 miles away, capture data analyzed by teams from Tokyo to Toronto, each bringing unique perspectives to interpret the planet's thermal secrets. At the forefront are planetary scientists like Lee Fletcher at the University of Leicester, whose work on ice giant atmospheres helps decode how Neptune's storms redistribute heat. Then there's Sabine Stanley at Johns Hopkins University, whose models of planetary magnetic fields shed light on how Neptune's lopsided dynamo might generate internal warmth. These researchers don't work in isolation, they're part of a sprawling network, sharing findings through consortia like the International Space Science Institute, where hypotheses are stress-tested by peers from dozens of countries. Laboratories worldwide contribute pieces to the puzzle. In Japan, teams use high-pressure devices to simulate Neptune's interior, observing how methane transforms into diamond rain. Meanwhile, at the Lawrence Livermore National Laboratory in California, lasers recreate the planet's core conditions, revealing how exotic states of matter like superionic ice might behave. This isn't just parallel research, it's a synchronized effort with data flowing freely across borders. When Stanford scientists confirmed methane could form diamonds under Neptune-like pressures in 2020, their breakthrough built on decades of German and French theoretical work. The push for future missions underscores this unity. NASA proposed Triton flyby and the European-led Neptune Odyssey concept, currently under study, are designed with input from scientists in India, Brazil, and beyond. Even amateur astronomers play a role. Their telescopic observations of Neptune's brightness variations, logged in global databases, help professionals track long-term atmospheric changes. What makes this collaboration so powerful is its diversity of thought. A physicist in Russia might approach Neptune's heat through the lens of quantum mechanics, while a chemist in South Africa explores hydrocarbon reactions in its atmosphere. Together, these perspectives weave a richer tapestry than any single team could produce alone. And as new telescopes come online, like Chile's extremely large telescope, set to peer deeper into Neptune's storms by 2030, the global effort only intensifies, proving that some mysteries are too vast for anything less than worldwide curiosity to solve. Neptune's heat mystery isn't just a scientific puzzle, it's a gateway to inspiring the next generation of explorers. In classrooms from Tokyo to Toronto, educators are using this icy giant's enigma to ignite curiosity about planetary science. Picture a group of middle schoolers huddled around a simulation, their eyes widening as they watch methane transform into diamond rain under extreme pressure. Or high school students debating why Neptune burns so fiercely while Uranus remains frozen, their theories as vibrant as the planet's blue hues. These aren't just lessons, they're launchpads for lifelong fascination with the cosmos. One standout example is NASA Ice Giants Challenge, where students design hypothetical missions to unravel Neptune's secrets. Teams compete to create orbiters, probes, or even drone concepts capable of surviving the planet's supersonic winds. The winning entry from a group of Norwegian teens proposed a fleet of inflatable sensors that would ride Neptune's storms like cosmic surfboards, relaying data from deep within its atmosphere. It's not just creative, it's a testament to how Neptune's mysteries push young minds to think beyond textbooks and into the realm of real-world problem solving. Universities are getting in on the action too. At MIT, a graduate-level course uses Neptune's thermal imbalance as a case study for modeling planetary interiors. Students tweak variables like core composition and atmospheric dynamics in supercomputer simulations, watching as subtle changes produce wildly different heat outputs. The takeaway: there's no single right answer. Just like in cutting-edge research, students learn to embrace uncertainty and iterate. One alum, now a planetary scientist at Caltech, credits the course with shaping her approach to studying exoplanets. Neptune taught me that the weirdest data points often lead to the biggest breakthroughs. But you don't need a lab to join the exploration. Amateur astronomers worldwide contribute by tracking Neptune's brightness fluctuations, a project that's helped identify new storm systems. In Australia, a retiree with a backyard telescope recently spotted an unexpected glow near the planet's south pole, a finding later confirmed by the James Webb Space Telescope. Stories like these prove that Neptune's allure isn't confined to academia. It's a global invitation to wonder, observe, and discover. The ripple effect extends beyond STEM. Art students paint Neptune's swirling storms, their brushstrokes capturing the chaos Voyager 2 first revealed. Writers craft stories about diamond oceans and hidden seas, blending science with imagination. Even musicians get involved, like the composer who translated Neptune's infrared data into an eerie, pulsating symphony, each note representing a different layer of the planet's heat signature. What makes Neptune such a powerful teaching tool isn't just its scientific intrigue, it's the way it embodies the spirit of exploration. Every unanswered question whispers to students, "We don't know yet, but maybe you'll be the one to find out." And that's the real magic. Whether through a telescope, a simulation, or a sketchpad, Neptune's mystery doesn't just educate, it inspires, proving that the universe's greatest lessons often come wrapped in enigma. Now we've explored the wildest theories, from diamond rain to dark matter, but here's where you come in. What's your take on Neptune's fiery secret? Maybe you think it's all about that churning ocean of superionic water, or perhaps you're convinced Triton's tidal tug is the unsung hero. Whatever your hunch, drop it in the comments. This mystery is far from solved, and your idea might just spark the next big breakthrough. Think about it. Some of science's greatest leaps started with someone daring to ask, what if? Back in the 1980s, when Voyager 2 first spotted Neptune's heat surplus, even NASA's top planetary scientists were stumped. Fast forward to today, and we're still piecing together the puzzle. That's the beauty of space mysteries. They're not just for experts in lab coats. Whether your team, helium rain, or suspect some quantum quirk we haven't even named yet, your perspective could shine a light on something everyone else missed. And hey, no theories too out there. Remember, the idea of diamond rain sounded like sci-fi until lab experiments proved it real. Maybe you've noticed a pattern in the data that's been overlooked, or you've got an analogy that makes the math click in a new way. Even if it's just a gut feeling, share it. Science thrives on collaboration, and sometimes the most unexpected voices spot the threads worth pulling. So hit pause, let those gears turn, and tell us, what's really cooking inside Neptune? Is it a combo of gravitational squeeze and stormy chaos? Or is there a cosmic wild card we haven't considered? The comment section's your lab. Let's dissect this enigma together. Who knows, your thought might be the missing piece that helps crack one of the solar system's coldest cases. Neptune's fiery secret remains one of the most captivating enigmas in our solar system, a cosmic riddle wrapped in swirling blue clouds and supersonic winds. Every theory we've explored, from the glittering cascade of diamond rain to the slow-burning embers of its primordial birth, feels like a piece of a puzzle we're still assembling. Yet, even with cutting-edge telescopes, supercomputer simulations, and lab experiments that recreate the planet's extreme conditions, Neptune refuses to give up its final answers. That's the thrill of planetary science. The closer we get, the more questions emerge, each one pulling us deeper into the mystery. What makes this puzzle so extraordinary isn't just the heat itself. It's what it reveals about how little we truly understand the inner workings of planets, even in our own cosmic backyard. Neptune defies expectations at every turn. It shouldn't be this warm, this active, this alive, so far from the sun's embrace. And yet, there it is, radiating energy like a cosmic rebel, challenging textbooks and inspiring bold new theories. Whether it's helium rain quietly releasing warmth as it sinks or the churning dynamo of a supersonic ocean generating friction, each possibility stretches our understanding of physics and chemistry in ways we never anticipated. The quest to solve this mystery isn't just about Neptune, it's a gateway to the universe. Ice giants like this one orbit countless stars beyond our solar system, and unraveling how our own behaves could unlock secrets about worlds light years away. Imagine peering at a distant exoplanet and recognizing the same thermal signature, knowing it might hide diamond storms or sloshing metallic seas beneath its clouds. Neptune is our prototype, our Rosetta Stone for decoding these distant giants. And while we wait for missions like Triton or the Neptune Odyssey to bring us closer to the truth, there's something beautiful about the uncertainty. Science thrives on the unknown, on the gaps in our knowledge that push us to think bigger, dig deeper, and question everything. Neptune's warmth isn't just a scientific anomaly, it's an invitation. An invitation to keep exploring, to stay curious, and to remember that even in a universe we've studied for centuries, there are still wonders waiting to be uncovered. So what's next? Maybe the James Webb Space Telescope will spot a new thermal anomaly, or a lab breakthrough will reveal an exotic form of matter we've never considered. Or perhaps, just perhaps, the answer is something nobody's even dreamed up yet. That's the magic of discovery. Until then, let's keep the conversation going. Drop your wildest theories in the comments below. Do you think we've missed a key clue? Is there a process at work we haven't even named? And don't forget to like and subscribe for more deep dives into the universe's greatest mysteries. The cosmos is full of surprises, and we're just getting started.